or that the data is even going to arrive there. It's stateless, in other words, and it's more message-based as opposed to a stream of data.
Awesome. Sorry, I was distracted there for a moment because apparently I didn't have us live on YouTube. So anybody who's joining us, I apologize. This is Adam Woodbeck who's speaking with us. He's the author of Network Programming with Go, and he's here to talk to us about TCP and UDP. So I apologize about that. I don't know why it didn't go live before, but we're good now, right, Chris?
Yeah, we're good.
Right. Awesome. Okay, so we were just talking about TCP and UDP, and you were explaining, sort of at a high level what they do. For anybody who just joined us, do you mind doing that again, Adam?
Yeah.
I apologize.
No worries. So TCP is the transmission control protocol, and it's probably the most predominant protocol you're going to encounter on the internet. It ensures reliability, it's stateful, and it's stream-based. So I can send a bunch of data to a remote server, and it can respond that it received all the data that I sent. And if it doesn't receive all the data, it can let me know how much it's received, and then I can turn around and send only the parts that it's missing. So it's very reliable. It's typically what you're going to see for the web, file transfers, a lot of things like that. For UDP, on the other hand, that's the user datagram protocol that is stateless. And essentially it's like just throwing data at the other end. And there's no guarantee that it's going to be received. There's no acknowledgement, but it's very simple, very fast. So usually UDP is good for real-time things like audio or video or first-person shooters, that type of stuff.
That's something that's probably, I think, confusing to a lot of people, because when you talk about like sending data, especially with programming, you usually think like all of it needs to get there. Can you give some, I guess, a little more insight into why UDP works for things like games where, real time is more important and they don't necessarily, how do they get by without having all the data?
So I would use UDP in the scenario where it's worse if a packet arrives late than if it doesn't arrive at all, right? So if I'm playing a game, for instance, a first-person shooter, I need to know where that opponent is, not necessarily where he was 2 seconds ago when I lost that packet, right? Or in this case, if we're talking back and forth, if packets are being dropped and you're not receiving all of the audio that I'm saying right now, then you're going to start talking to reply, and now you're starting to get all the words that I just said as TCP catches up. So UDP is more concerned about getting the data to you immediately, even if it's not complete.
Okay, that makes sense. That's I'm trying to think of, I don't know if it's video software or what, but I recall using something where like when somebody would start to lag, you'd all of a sudden see them catch up. And it was always a really weird experience when like their video stream would sort of like quickly replay back everything or something. And I'm guessing that was because they were using something like TCP to sort of replay back what was there. Whereas, a lot of times what we normally experience with Zoom is if somebody starts to have some sort of internet connection or something, they just sort of cut out for a minute and then come back in. Is that accurate?
Yeah.
Or sound accurate?
Yeah, it like with real-time stuff, you don't have the advantage of buffering either, right? So TCP is really good at buffering data. And so in the scenario you just outlined, they were probably catching up with everything that was coming in off the wire, just reading it. And so it looked like it fast forwarded to real time at that point, right? When in the user experience probably would have been better if we just dropped those packets and you just picked up from where they left off.
That makes sense. So I guess let's dive into TCP first, because I think this is the one that people are going to relate to most, at least in my experience. I feel like most of the things I do networking wise are TCP. So that's where I'm starting. So if you're not the same as me, sorry, everybody listening. You said that TCP is something where they can actually have a session where packets aren't lost. What does that look like? Like, what does the connection look like? What are the steps? And I guess, how does that sort of work at a high level?
So there's let me use an analogy first. So TCP, let's say you're going to bake your neighbor a pie. Okay. If we were doing this over TCP, then I may shout from my window to my neighbor's window to say, hey, are you there? And my neighbor may reply and say, yes, I'm here. And then I'll say, I'd like to bring you a pie. We've just established a conversation, right? And so the neighbor acknowledges and says, great, bring it on over. So I bring the Pi over. Okay. And then I say farewell. Neighbor says farewell. Conversation's done. Okay. That's TCP. That's our stateful conversation. Now, if I was doing the same thing over UDP, essentially I would take that Pi and I would throw it at my neighbor's window without any regard for whether the window's open or not. Right. And I have no idea if my neighbor received it. It's very possible that my neighbor is going to be quite upset with me. So that's kind of the high level difference of what one protocol looks like and what the other one looks like. One, there's a lot more back and forth, but there's reliability there. There's a conversation, there's a rapport, I guess. And the other one is just very abrupt. Here's data, hope you get it, do something with it. So to add reliability to UDP, you have to do that in your application. So we're just simply talking about the transport layer right now. Okay, so this is below the application. When you write something to a network socket in Go, you're essentially writing it to the transport layer. And this is where TCP would take over, or UDP would take over. So there's a lot of stuff that happens underneath at this layer that you don't have to account for in your application. So if we're talking about, like, say, a web request, I visit Google, for instance, then what that would look like is my computer would reach out to Google. It would open up a port on my computer, a local port, and it would reach out to Google at Google's IP address, port 80. Let's just say there's no TLS involved here. So port 80, and that now establishes a unique connection. It's a 4-tuple, right? So it's my IP, my port number, Google's IP, and Google's port number. There's no other connection right now that has those 4 components. So this is unique. So then my computer sends a empty packet, essentially, with just header information to Google, and it has a SYN flag enabled, or synchronize, which is essentially telling Google, these are the settings I would like to use for this conversation I want to have with you. So if Google wants to talk to me, then Google will turn around and it will send back a packet, an empty payload with just header information that has an acknowledgement that says, I acknowledge I received your SYN packet, and here's a SYN of my own. Here's what I agree to as far as this conversation goes. And then if my side agrees, it will send an acknowledgement back. So an empty packet again with just the acknowledgement flag flipped. So that's the 3-way handshake that all TCP connections start with. Okay. From that point forward, we have an established session and data can flow in either direction. Once we're done exchanging data, then usually there's a graceful termination where either side can initiate this, but let's just say I do. I would send a FIN packet. Essentially, it's an empty packet with just the FIN flag flipped. Google side will acknowledge that and say, all right, I acknowledge I received your FIN. Here's a FIN of my own. And then I would acknowledge that, and essentially the connection is terminated at that point. There's no more active TCP connection.
So to make sure that both myself and everybody listening understands, like when I make a web request to google.com, is this something where like the entire time the page is open, it's keeping the connection, or is this something where it just keeps the connection open long enough to, get the website HTML and then after that it closes up? Or are there cases where it's a little bit of both?
So TCP has keep alives, which I believe are off by default in most of the operating systems I've used. But what essentially would happen, let's say I send a request to Google and it's taking Google a long time to respond. There's a lot of latency there. Maybe it's having to crunch a bunch of numbers and stuff and then send the response back to me. My side may send a keep alive request, which is a special request to Google's network layer, its transport layer. It doesn't go to the application. It just goes to the TCP layer at Google to say, hey, is this conversation still good? Are we still talking? And then normally I would get an acknowledgement back, which essentially tells me, yes, we're still good. I just haven't received your reply from the application layer yet. And this may go on for a while until either I receive a reply or we've reached some sort of threshold and I just stop waiting and tear down the connection that way.
So when we talk about having these communications that are, back and forth with different messages, I think most of the time when we think about like a web request, we think of like I send a request, they send a response back with all the data. I'm assuming that TCP because we're at a lower level, it's probably something where there's maybe a little more back and forth than that. So I guess my question is like, how does the actual data sort of get transferred at that level? Is it like a binary encoding? Is it something completely unique? Or, what does that sort of messaging look like?
Okay, so I think we should talk about a few of the things that were established during the handshake, okay, that help ensure the reliability, and it helps control the flow of information between the boxes. I said earlier that TCP is a stream-based protocol. So if I'm sending a web page to you, or I'm sending a bunch of data, it comes through as a bunch of bytes. And there may be that those bytes may be composed of several different individual messages, right? But my side, when I'm reading from this data, I'm just getting a bunch of bytes and have to make sense of it. So we can talk about some methods of how you can properly encode things so each side can encode and decode the data that we're sending. But as far as a web page goes, there's what's called a sequence number that each side establishes as part of the handshake. It's usually a large number. It's usually only meaningful in the session itself. But for our purposes, let's just say it starts at 0, because that's an easy number for everyone to remember. So when the client sends the first SYN, part of that SYN has, it tells the server, I want to start with sequence number 0. Okay. When the server acknowledges that, even though the packet, the payload was empty, there's what's I've seen termed a ghost byte, right? So the server acknowledges a sequence number of 1, essentially saying that the client sent 1 byte, even though it didn't. So just bear with me, it's a ghost byte, okay? The same thing happens in reverse. When the server sends the SYN ACK, it says, I'm going to start my sequence number at 0. In reality, it's a large number, right? 0 for our purposes. And then the third part of the three-way handshake is my side sends the acknowledgement of sequence number 1. So now both the sequence number on both sides is set to 1. So the acknowledgements acknowledge sequence numbers, which is one of the ways that we ensure reliability here. So if my GET request for the resource was 500 bytes, I send the 500 bytes in a request to Google. Google then sends an acknowledgement back of sequence number 501, because this sequence number is incremented by the number of bytes that I'm sending. Okay, so Google's sequence number is still set to 1 because it didn't send me any data yet. It just sent me an acknowledgement. So when Google sends me the payload that I requested, let's say it's 2000 bytes, it sends me all that data and I acknowledge a sequence number of 2001. Okay, so that's, if I acknowledged, say, 1001, then Google realizes, wait a minute, he didn't receive the last 1000 bytes. I should resend that. Okay, so that's one of the ways we ensure reliability and kind of keep track what was sent and acknowledge what was sent. Now, the other factor here is that's negotiated during the handshake is the window size. So every TCP connection allocates a certain amount of RAM that it's going to use as a receive window. Think of it as like a bucket. Okay, so what this allows is it allows me as the sender to send data to Google that sits in that bucket, and the application can then come and read. The application doesn't need to be actively reading from the socket at the time I'm sending data. It can sit in that bucket. But I don't want to fill up that bucket, because if I do, then anything I try to put in once the bucket's full just gets thrown away, gets lost. So in this case, let's say, and we may be getting too far into the weeds here if we want to talk about window scaling and stuff, but essentially I send the request in an attempt to fill the bucket, and there is a maximum packet size that I can send for each request. For our purposes here, the maximum segment size will be 1460, let's say, which means the maximum packet size is 1500 bytes. because there's a 20 byte header for TCP and a 20 byte header for IP. Okay, so every request I send or every request or every response that Google sends can be in these chunks of essentially 1,460 bytes of data at a time. So if I request something that is 2,000 bytes, then I'm going to get essentially two packets. One's going to be 1460. The second packet is going to have the remainder of the bytes. So I keep getting this in these chunks at a time until either my bucket is full and I can't accept anymore, or until I got the entire payload that I requested at the time.
So when you're talking about these buckets that the bytes come into, I assume that's just the buffer that, like, when we're in our actual code, if we start reading the incoming data from Google, at that point it would like clear out the buffer and it would get emptied up again. Is that correct?
Yes. So essentially, if I'm receiving data from Google and I never read that from my connection, then it just sits in that bucket, and the bucket could eventually fill up. And then my side's going to start telling Google, don't send anything else. I have no room for you to send any data to me. So the onus is on me and as the programmer to make sure I'm reading data from that bucket so I can continue to receive more data from Google.
So as a developer, this is something that we never really see in our code. Like, none of us are sitting here writing HTTP requests where we're like, okay, we're going to send 100 bytes, then 200 bytes, whatever the limits are.
Sure.
So I'm assuming this is all something that, like, the standard library and everything sort of bakes into it. Is this something where every language could sort of decide how they're going to change? Like you said, if your max is 1460 bytes, I'm assuming that arguably you could send less than that if you wanted.
Absolutely, you could.
So that's like up to the programming language or whoever wrote the library to sort of decide how to choose those numbers?
So there's defaults for your operating system, but we're talking about every hop along the way between my computer and Google. This maximum size is enforced along the way. The good thing about TCP is we can split things up and it can reassemble things. Packets can be received in the different order than I sent it on the remote side, and TCP can straighten all that out for the application. So with like UDP, we don't want things to split up. We want to stay under that size limit so it doesn't get split. But with TCP, I can send a bunch of stuff. I can send a gig of data if I wanted to. And TCP is going to handle chunking that up for me, sending that data across. And of course, the other side is going to handle reassembling everything into the stream as I originally sent it.
You mentioned that the data can basically come out of order. So when you were talking about your analogy of, yelling out your window at your neighbor and having a conversation, having the conversation go out of order isn't something that most of us, it's not something that's really logically going to happen with a conversation.
Correct.
So with the network, I think sometimes it's easy to overlook that because you just assume, okay, these things are going serial, especially with a lot of programming. Until you get into concurrency or something, things happen serially. So
Sure.
can you elaborate a little bit on, like, how do things get out of sync? What are some ways that might happen?
Okay, so you could have the scenario where one packet takes one path to Google and another packet takes a different path. I don't have a direct cable from my house to Google. So there's not just one destination to Google. We're talking about the internet. So it's essentially a mesh. I mean, I can send a packet from here to my ISP, and my ISP can send it to, different endpoints, and it keeps moving its way through the internet, the shortest path that it can until it reaches Google. And that shortest path may change depending on the metrics at the time the packet is traversing the network. So I'm not guaranteed that all the packets I send are going to go over or take the same path as the packets before it. They could take another path. We could be sending data, communicating, and a tree falls on a line and takes it out, or someone snips a fiber optic cable that I was communicating, and now those packets have to go some other way. So they're not guaranteed to arrive in the same order, but when they arrive in the receive buffer, TCP on that end starts putting them back in order before it makes those available to the application to read. And if anything is missing, then TCP will request, it'll send me a request to say, hey, I got everything but this set of packets here. I need you to resend just these. So, and that's technically selective acknowledgements, which we didn't really cover yet, but.
And I
So
think as well with that, packets can get routed differently, but they can also just get dropped. So
Absolutely.
if some network
Yeah.
device in there is just overloaded, it might just be like, I'm going to drop all these packets because I can't handle, I can't process them right now. And that's perfectly valid to do in IP. So TCP, as Adam just mentioned, can ask for packets to be resent. So that's how you could also get them out of order.
Sure. Yeah, there is limitations to how much data switches and routers can handle. And if they are overloaded, they just drop it.
I think one of the things that's really cool to see about TCP is that we talk about building redundant systems, but like this is one of the most redundant systems. Like if you think about it, or at least it seems like one of the more redundant systems that we deal with on the internet is the fact that literally anything can just stop taking packets and everybody knows how to sort of handle that and move forward.
Yeah, I mean, think about, and I don't have a lot of experience with this, but think about if you're watching a YouTube video and you're driving in your car and you're watching it on your cell phone, you're hopping from tower to tower and you're getting different IP addresses, yet from your perspective, TCP is able to handle all of those different changes and interruptions and properly buffer things as it needs to. So your playback is nice and smooth.
So speaking of that, and I don't know if this is too complicated, but how did the TCP connections work when you're doing that? Like if we're driving down the road, is it making new connections?
Like I said, this is a little outside of my experience, but the way I envision something like that would happen is if you're hopping to a different tower and you're getting a new IP address, your application realizes where it left off as far as what frames it just requested from YouTube. And when it establishes that new connection, it may ask for the frames from where it left off. But if you ever watch your YouTube progress bar, you'll see that it buffers. In other words, it's downloaded more of the video than what you're currently watching right now. So it's giving itself some buffer room here at the application level.
And I think too, with mobile networks specifically, there's a lot of magic they do behind the scenes to make it appear as if the TCP connection is kind of living forever. And we'll probably talk about it later, but this is one of the reasons why HTTP/QUIC was developed, mainly to resolve this problem of TCP connections being at odds with how mobile networks operate.
Which is, I mean, it's kind of interesting because when people design these things, it's impossible to see into the future. And I imagine at the time it was probably impossible to imagine this world where somebody's driving down the road and literally like that needs to pretend like it's one connection when in reality it's not. So that's one of the crazy things about software, I guess, is that you can never really predict what you need to design for in the future.
Sure.
Okay. Let's say I wanted to dive into this a little bit more. I wanted to actually see some of these bytes. What's some way that I might be able to do it? Should I start with Go code? Should I be looking at tools to watch my networking traffic? What would you sort of recommend on that side of it?
I absolutely recommend you familiarize yourself with Wireshark. It's an essential tool if you're writing network code and you want to see what's happening at that transport layer. Wireshark is great as far as it's free, so it's very easy to install on your system and then run. I mean, just install Wireshark, start a capture, and then in your browser go to a website. And you'll see all of this traffic start flooding into Wireshark. And you can use Wireshark to filter in on a specific conversation. And you can see that three-way handshake that we talked about. You can see the sequence numbers that they established and how those sequence numbers and acknowledgements work, similar to what we just described, and how the graceful termination happens for every web request that you make, for every resource that you ask for.
Okay, so go check out Wireshark, everybody. If you have questions, bug Adam. No, I'm just kidding.
Yeah. There's a good book on that. No Starch also sells that, so that's where I'd refer you.
Okay, awesome. When you were talking about TCP, you mentioned that it's streaming bytes, and usually when we're sending bytes, like we have to get into some sort of encoding, sort of letting people know how big bytes are. Is that something? I guess who controls that? Is that something, and like what does that look like?
So let's say I wanted to send a string over a network. I could just, or I wanted to send, let's say I wanted to send a string, or I wanted the ability to send numbers as well, or different types. And essentially what I'm doing is I'm writing a byte slice to the network. And when it's received on the other side, it just reads a byte slice. Now, all the other side sees is it's just a series of bytes. It doesn't really make sense or know that this is a string or how big the string is, because when I'm reading data from a network, I essentially allocate a byte slice of a certain size. And when I use that byte slice to read into that byte slice, the network will try to read as many bytes as it can that's in my buffer to fill that bucket, essentially, that buffer that I created, either until we run out of bytes to read or until that buffer I allocated is full. So if I send several strings at once to you and you start reading them from your network, they're all going to be in that same buffer, that same byte slice. You don't know where one starts and one stops. So one technique that works well is very simple encoding, such as like a type length value method of encoding data, where you say, all right, we're gonna say this first byte is going to represent a type. 1 for string, 2 for an integer, whatever bytes you want to encode. The next 2 bytes or the next 4 bytes will represent the length of the payload I'm going to send, and then the remaining bytes are that payload. So when I'm reading data from the socket now, I can read the first byte and realize, okay, this is a string. I can read the next 4 bytes and then, convert that into an integer and say, all right, he's sending me, I don't know, 500 kilobytes of data. And then I know I need to read the next 500 kilobytes of data, and that's my string, if that makes sense.
Yeah. So I guess in my mind, that means that if I'm writing my own, for lack of a better word, like client and server that are communicating, I can sort of define this paradigm myself, where I can say these many bytes are the type, these many bytes are the size of the message, and then I can just go from there. So does that mean there's standards for things like the web or different places like that everybody just sort of agrees to? Because, obviously I'm not writing Google server, so I can't tell them what to expect. So is that how the web works? Is there some sort of standard there?
Yeah. So when you're requesting a resource, say you're requesting a web page, just an HTML page, you're going to get header information back that'll have your content length, and that's essentially the length of the payload that's going to represent the HTML that you requested. For instance, there's other encoding methods like gob. Go includes gob in its standard library, and essentially it can do what we just talked about, as far as I can instantiate a struct and send that across the network, and it can be properly decoded on the other side using a similar type length value format that we just discussed.
But is this something that like both people sort of have to know about ahead of time, or is this something that's communicated during the handshake, is what I guess I was trying to ask? No,
you have to agree on the encoding and decoding standard that you're using. So in other words, if I'm sending you JSON, for instance, you need to know that it's going to start with an opening curly brace and end with a closing curly brace. You have to understand the garbled text I'm sending you. You have to be able to understand JSON. But if I sent you like YAML, for instance, and you're expecting JSON, you're not going to know what to do with that. It's not going to look, it's not going to decode the way you expect it to decode.
Okay, awesome. So when we're dealing with these network connections, I guess another question I have is TCP is, you basically said it's sort of like this conversation we're having. Is that something that we need to close? Because with UDP, I assume you just sort of send your message, forget it, don't worry about it. So with TCP, do you have to worry about telling people essentially goodbye in the conversation, or how does that sort of look?
Yeah, so programmatically in Go, when you have a network connection object, it has a close method. If you do not call that close method, your side of the conversation doesn't send its fin. It doesn't tear it down. It can keep your side of the conversation open, and you're essentially leaking the connection. And so if you do that enough, you can exhaust the number of connections that your operating system can open. And now you can't open any more network connections because you have all of these essentially orphaned network connections that are in a what are called a closed wait state because you didn't properly close them in your code. With UDP, you don't have to worry about that.
So I guess the next thing might be to talk a little bit about UDP.
I have a question on TCP first.
Okay.
So you mentioned sequence numbers with packets and how we increment them for the number of bytes. I guess how are those represented? And if they're represented with some fixed sized, fixed number of bytes, what happens if it rolls over, right? If we pick a random number and then we try to send, if it's like 32 bytes, 32 bytes, and it sends like 4 gigs or 5 gigs of data over the TCP connection, does it just wrap around and we just start from the beginning, or how is that handled?
I don't know. I mean, I honestly would have to look at the limitations of what the sequence number is, the size of the sequence number. It is a very large number. I would be surprised if you did overflow it. But I assume if it's unsigned, it would just wrap around and continue where it left off. But essentially, it only serves to as an indication of how much data I've sent you and how much data you've received. And we need that agreement there. So if I send you 5,000 bytes of data, I expect an acknowledgement that is 5,000 more than the last sequence number I sent you.
Okay.
Now, if that happens to roll around, then or overflow, then so be it. As long as it's 5,000 more than what we had before.
Yeah, that could be interesting if, or it could be like a weird case for a bug if everybody sort of stores that separately and one end sort of gets it wrong. But it's hard to say how that actually works.
So you can see this in Wireshark. Wireshark, it does a lot of very friendly things for you. Like it'll calculate your window size for you. Everything in Wireshark that's in square brackets is something that Wireshark calculated based on the packet you're looking at. And so the sequence number, the raw sequence number may be in the, so it is 6 bytes. That's how many bytes we have for the sequence number here. But when you're looking at it, Wireshark gives you a relative sequence number starting at 0, just like we discussed here. So it's easier for you to rationalize when you're looking at the packets. If you wanted to see the raw sequence number, you can do that too.
So I got curious. So I'm sitting here on Stack Overflow looking this up, and it looks like it is a 32-bit number, Chris. Oh. And it seems like, generally speaking, you're supposed to sort of choose a starting sequence number that you theoretically wouldn't go over that limit. But it almost looks like it sort of wraps around if it needs to, and they use timestamps to sort of make that work. But
yeah,
you would have to send a tremendous amount of data in order to.
I mean, it's 4 gigs,
yourself, right?
Because it's that'd be like 4 billion bytes. It's about what you can represent with a 32-bit unsigned. So that's like, I mean, if you're downloading a 10 gig, I don't know, application or something, or video file that's over a TCP connection, you can see it wrapping around.
Yeah, that's an interesting one because we've gotten to this point where 4 gigs isn't that much. Like it used to be a lot, but now it's like you download video games that are 30 gigs or something pretty regularly. Well, maybe not, but if you're a gamer, you probably download 30 gig games somewhat regularly.
Yeah.
So yeah, that would make it very tricky. I mean, that's another one of those cases where I could see when they originally designed TCP, they're like, oh, we'll never hit this number. Don't worry about it. And then later they're like, we need to figure something out here.
Yeah, like IP4 addresses, IPv4.
I didn't know if we wanted to talk about that today or not, because I think if I recall correctly, wasn't TCP and IP all one thing at the start?
Yeah, it was called, was it Transmission Control Program, I believe, until they ended up splitting TCP from IP. And then since they abstracted TCP from IP, they were then able to implement UDP as well. But yeah, TCP and IP used to be one monolithic protocol way back when.
It's nice that they had the foresight to figure out separating that one.
Yeah.
Otherwise, it'd be pretty rough trying to upgrade TCP to V6, I guess. Okay, so I guess the next thing we want to talk about is UDP. We've talked about TCP where you've got this, I don't know if we use the word stateful, but I assume that is like a stateful connection because you have to keep track of how many bytes have been sent and all this information about the conversation. UDP, you've said it's just sort of sending messages. What does that look like in practice? You know, obviously we're not just going to randomly pick an IP address and just send it random data. So can you give some examples, I suppose?
Sure. DNS is probably one of the most common uses of UDP that most people will encounter, even if you're not aware of it. And essentially, that is where I'm sending a UDP packet that usually has a maximum size of about 512 bytes to a domain name server, asking it for an IP address, for instance, for say google.com. And it would normally reply with my answer. And if it doesn't reply, because I don't get an acknowledgement back that it received my request, I simply just get an answer or I don't. And if I don't get it back in a timely manner, then I'll ask again and again until I get sick of asking or I get a response. But if we look at that, what would that look like with TCP? If we were making that same request with TCP, we would have to go through our three-way handshake. I would have to send a request, which it would acknowledge. Then it would send a result, which I would acknowledge. And then we would tear that connection down, right? So many more back and forth requests, a lot more overhead if we were using TCP for this. But for UDP, considering we're talking about a small amount of information, less than 512 bytes in most cases, there's exceptions to that, of course, UDP is perfectly suitable for that. I just send a request and get an answer back and keep asking until I get what I'm expecting.
So I guess one way to look at this, going back to your sort of pie analogy, is that if you're bringing somebody a pie, you kind of want them to acknowledge that they're there to pick it up. You don't want to have a pie sitting on their doorstep. But if you, let's say their mail happened to be in your mailbox, if you just wanted to walk it over and slip it in their mail slot, you don't really need acknowledgement that they've received it or anything. It's just slip it in there and sort of forget about it because it's not something that you really care too much about. You know, you don't need to have a 5-minute conversation to sort of give them their mail piece back.
Sure.
And I assume, like you said, one of the major benefits for DNS using this is the fact that most of the time, if you just do 2 messages, like one to say, give me this information, 2 to get the information back, that's a lot better than, you know, doing that whole handshake, wasting a bunch of time, having a conversation that you didn't need. So if I wanted to go about doing this in some Go code, what might that look like? Are there packages or anything, or would you suggest, again, just using Wireshark? Like, what are some ways to sort of experiment with UDP?
Go has good support for UDP. And in fact, you can, if you've used UDP, if you've used TCP and Go code, you're probably familiar with in the net package, there's the con interface. And if you use the dial or dial timeout, or the dialer in the net package has a dial context function or method. When you call that, you receive a con interface back that allows you to do a few things. You can write to the network socket. You can read from it. You can change the deadlines, which we haven't talked about yet, and you can tweak a few things in the connection through that interface. You can also do a type assertion to the TCP con struct, the object underneath that interface, and it gives you a lot more options that you can do. A little bit. You can then start modifying, say, your receive window, your send window, and other things like that. Enable keep alives if you want to. I would think for most purposes, though, the con interface is suitable for most people using TCP. Now, the reason I bring that up is because when you use the dial function in the net package, you can specify a network type of UDP as well, and you still get a con object. However, there's an underlying UDP connection to that con interface now. So, and it's going to function a little bit different. It's still that object, although UDP is stateless, the object is maintaining, it knows who it's sending to. In other words, when you create this connection object, even though it's UDP, you give Go an address that you want to communicate with. So when you write to this object, it will only write to your destination. And when you read from this object, it will only pay attention to UDP packets coming from that destination. Now, there's a packet con as well, and that's probably better suited for UDP, at least the way most people will use it, because the difference with TCP and UDP in Go is TCP has a separate client that dials or reaches out, and then a listener, right, that listens for incoming connections. UDP isn't like that. When you establish a UDP object, it's both a client, if you will, and a listener. It's listening on a local port, on your computer, and anything on the network can send messages to it. So when you read data from that UDP connection, you get the amount of data you read, you get an address and an error interface. And so you, as the programmer, need to check and see, okay, I need to look at this address. Who did this come from? Because it may not necessarily come from the destination that you're communicating with. It could have come from a third party potentially. So there's more work at the application layer to manage the incoming data through a UDP connection if you're using that packet con.
I have a question about how the operating system handles data. So with TCP, we have like this established connection. So it has this receive window. So if bytes come in, it just holds them for you until your application reads them. Is there a similar mechanism for UDP? Or if it gets bytes, it just kind of like, if you're not listening, I'm just going to toss them away.
So UDP also has a receive buffer, but you don't know if you send data to a remote side, just like we don't know if your neighbor's window is open or not. We don't know if it's been received. We don't know. It could be sitting in the receive bucket over there, but we don't know how much is in that bucket. So we could be filling up the bucket until it overflows. And when it overflows, your UDP packets start dropping. And so you don't get that indication back at the UDP level on how full the remote side's bucket is. You can keep sending and hopefully they're reading from it. Otherwise, you're going to start dropping these packets. But there is that same concept of a receive buffer.
So I have a question about the net.con interface. And at least in my mind, a lot of times when you're using an interface, it's kind of meant to be something that's somewhat interchangeable. Like you might have an interface for interacting with your data store, and you don't really care if it's written in SQL or Postgres or SQLite or something else. Generally, you're like, I need this interface to interact with it. But it sounds like with TCP and UDP, you kind of get the same net.con, but at the same time, how you actually use them needs to be very different, because with TCP, like your messages are getting there eventually, but with UDP, that's very much not the case. Is that something that you think is confusing, or is that just? So I guess, what are your thoughts on that?
If you're very used to using that netcon with TCP, my personal preference is to not use it for UDP, because it does change the behavior subtly. So for instance, we talked about reading data from a TCP connection in Go. You create a byte slice of a certain size and you read data into that, and you will keep reading data into that until it's full or there's no more data to read, right? With UDP, it's different. If I send you 4 messages, 4 separate UDP packets, and they're sitting in your receive buffer, if you're using that netcon and you read, even if the byte slice you've allocated is large enough to hold all 4 of those messages, every invocation of read only returns 1 message at a time. So you would have to read those 4 messages, you would have to call read 4 times if we're talking about UDP, but that's not netcon's behavior when you're using TCP. So my personal preference is to use packetcon, and then it's very explicit that, all right, I'm using UDP in my code here. I can't just, it helps if I'm reading someone else's code too, to know that, okay, this is a netcon here. I'm very familiar with this because I use it all the time with TCP, but I didn't notice that they're communicating over UDP now. Why do they keep, why do they read this 4 times, for instance, when I think that the buffer they're allocating should be able to hold everything that they're reading once.
Yeah, that makes sense. I know another thing that that you sort of mentioned was, I think you said that whenever you're doing DNS communication, it's 512 bytes, I think is what you said for the message size. Does message size matter for UDP? Like you just said that you could have a buffer that could hold much larger things.
Yeah, so this goes back to the maximum transmission unit of 1500 bytes that you're likely to see on the internet. Okay, so this is the maximum size of packets that most routers and switches are comfortable transmitting. You can certainly have, these super packets that are much bigger than that, but 1500 is a good number to shoot for. So with UDP, whereas fragmentation in TCP is perfectly fine. So if your packet in TCP is traversing a router that doesn't support 15 MTU of 1500 bytes, it may fragment it. It may split it up for you. And then those will be reassembled later on. And you ultimately receive all of those fragments and therefore all of the data you sent at your destination. TCP, guarantees that with an acknowledgement. So UDP is not the same way. With UDP, we don't have that reliability at the transport level. So if there's any fragmentation, now each one of those fragments is subject to corruption, to being dropped, to just being delivered out of order, because there's no orderedness now, right? When we're talking about fragmentation in UDP. So you want to try to avoid fragmentation in UDP if at all possible. So normally what happens if I'm using UDP and making a DNS request and the response is going to be larger than 512 bytes, then normally the server will tell me that the answer is truncated. It didn't give me the full answer. So me as a client now, I know, okay, if I want the full answer, I need to repeat this query, but do it over TCP. And then I can repeat this query over TCP, incur the overhead of the back and forth and establishing the session and stuff, and then I'll get the entire answer. So really, the reliability that we rely on or just sometimes take for granted in TCP is not there in UDP, and you need to at least be aware of UDP's limitations in that regard, and then account for that in your code. Meaning, like, your code may need to, when you're sending data from your application, include your own sequence number in the data. And then on the other side, when you read that data, that message from the UDP socket, inspect the sequence number in your application and decide, this is the order I expected, or you manage the orderedness yourself, and then send a UDP acknowledgement. So the reliability that we have in TCP, you don't have with UDP, but if you need that reliability and the speed of UDP, the onus is on you, the developer, to add that reliability in your application itself.
Question about fragmentation. When the packet gets fragmented on the other side, do you receive that as like two different UDP messages, or is it like combined at the OS layer into one?
No, it's not recombined, is my understanding. I mean, even if it is fragments, and now we have, each fragment has its own checksum. It can be dropped, it can be corrupt. We've basically just taken a single packet and split it into multiple parts. And if any one of those parts is corrupt, dropped, or just goes missing, then you can't reassemble the original UDP packet anymore. The entire thing essentially is worthless, and you just need to resend it.
Okay.
That definitely introduces some complications to sending large messages that way.
Well, so there's like the protocol, trivial file transfer protocol. I don't know if, the only time I've ever used it is when I bricked a Wi-Fi router, and it was the only way I could load firmware on it was using TFTP, and that's UDP based. And it essentially has what we're talking about here as far as sequence numbers and acknowledgements, but that's again at the application layer. And I think it's chapter 7 in the book where you write a TFTP server essentially.
I think one of the interesting things about these network protocols is like, well, why did we develop TCP the way we did? And I think a lot of that has to do with network congestion and people just overloading networks. And when networks overload, like overloading them more, like that's why we have window sizes and all of these other things. I think it's interesting that we've gotten to a point now where those things have become more of a hindrance to us in some circumstances than they are a benefit. I think a really good example of that is the journey that HTTP has been on. We all started with HTTP 1/1.1, where it was a text protocol and you couldn't multiplex. And we had this head of line blocking problem. So you had to open multiple TCP connections to make browsers faster. And then we made HTTP 2, which added multiplexing, but it was still over an HTTP connection, it was still over a TCP connection, and immediately ran into more head of line blocking problems because TCP is ordered. So even if you have independent streams of things happening, if one gets blocked with processing or whatever, then all of the streams get blocked. And this protocol that was supposed to be magically faster actually turned out to be really bad if you had a really crappy network. And I think the other thing that we also started figuring out is that TCP works really great if you're not moving, right? If you are like a desktop or you're on Wi-Fi and you can establish this connection. But as soon as you're hopping between like Wi-Fi and a mobile network, now you have problems because with a mobile network, they kind of make it appear as if you still have a TCP connection. But if you switch to Wi-Fi, your TCP connections are now gone. You have to reestablish them, which is super expensive. So QUIC/HTTP3 is now giving us the ability to move those connections between things, right? You can go between a mobile network and Wi-Fi and keep your connections alive. But it's essentially just rebuilding everything we had in TCP on top of UDP because TCP is too restrictive.
Yeah, it's moving it all to the application layer.
One of the ones that's like that really stuck out to me when you said about HTTP2, Chris, was when you see web pages where they like put all the JavaScript at the bottom, like the include tags. I assume that's one of those things where if it gets blocked trying to load those, is that what you're referring to?
So it's more referring to if you have multiple files that you're trying to load at the same time, if one of those files is like taking a long time to process or whatever inside the HTTP application code, it will block anything else coming through. So if you're sending like a giant file and then like several smaller ones, but the way it gets put onto the wire is that like the last byte of one of those smaller files is after all the bytes of the larger file, you have to go through all of the bytes of the larger file before you can get to the byte of the smaller file. With UDP, since there is no inherent ordering of those packets themselves, if you get that smaller packet earlier, you can just go and process it. You don't have to read everything in the order that the initiator sent it. So that's the head of line blocking problem that usually people run into if you have shaky networks where you're dropping a lot of packets because you're just waiting for these packets to get redelivered to you or resent, and you can't read anything after the packets that are missing, even if they're not relevant to the thing that you're reading.
So when we were talking about the sequence bytes, I'm assuming this would be a case where like let's say we're at sequence number 1 and we get all the bytes from like sequence 3 to like 1,000, but we haven't gotten 2 yet. So we're like, we got to sit here and wait, to do anything with that data.
Yeah.
Okay. The other thing, Chris, you had mentioned, I think was HTTP3 and was it QUIC? Is that what you?
Yeah, HTTP.
So I know nothing about this. So if you guys want to talk about that, you are more than welcome to, but I cannot lead that part of the conversation.
So I guess we could probably start with just like an overview. I gave a brief one, I think, of why we wound up here. I think one of the interesting things about this is that you're probably already using HTTP3/QUIC. If you use Chrome and you connect to a Google service, most of that stuff is happening over this new protocol. But I guess the simple way to describe it is whereas HTTP 1 and 2 rely on TCP as the mechanism to order the bytes. So it just puts all the bytes on the wire in whatever format. There's framing in HTTP 2, so you can do that multiplexing. So if I have 3 streams that are sending data, I'll chunk them into smaller pieces, and as I'm ready to send them, I will multiplex them onto the TCP connection. HTTP3 is higher level than this. Like all of that ordering is at a higher level of abstraction. So instead of relying on the connection to give you any sense of ordering or to do the framing there, they do the framing directly in UDP, breaking up the packets to those sizes per stream, and then they have all of the identifying information inside each UDP packet as it's getting sent along. Yeah, I think I already mentioned that the biggest benefit to something like this is that you get that nice, I can switch different between different networks, and it still works because the connection information no longer lives within TCP, within that protocol layer. It lives within the application layer, so the application just has to know, oh, this is part of this stream that I already have. And I do want to say too that I think the interesting thing about this is that HTTP remains the same throughout, whether using 1 or 2 or 3. That is all abstracted from you. You don't have to worry about any of it. The way that you interact with it in most programming languages is the same way that you've interacted with any of the other ones, which is really cool and a really interesting design pattern. So while I think it's really interesting to like play around with TCP and UDP, building things, I think I would almost always go with HTTP unless there's a really good reason not to.
Yeah, I think that was one of the reasons why I wanted to do this episode, was that I think, generally speaking, most people are better off just using the HTTP package. But it's nice to sort of understand what's going on under the hood, because sometimes we don't get time to nerd out and actually just see like, how is this actually working? And that can be really cool and also inspiring for like if you have an idea to build something and just want to see how people built things in the past.
Yeah,
So
I think most
okay.
people should go and tinker with TCP and UDP and build stuff. Probably not for production with it. It helps you, I think, understand how all of this is working too. I think a lot of times it feels like this is all magical. Like, oh, TCP just handles everything for me. I've had situations where I had to debug an application and, we're like, oh, well, TCP always cleans up connections properly. There's never a state where you can just have a TCP connection stuck open. And we debugged an application and we had one side of the connection thinking it was still valid and trying to write for like 36 hours, and the other side had like killed that connection ages ago, and it caused a massive problem within our applications. But people that knew how TCP worked were like, that shouldn't be possible, but we had the ability to look at it and see, okay, this is happening, and implemented a timeout to make it so it didn't happen again, or probably a deadline, not a timeout. But I think like understanding how this stuff works demystifies it a lot, so you can wind up being able to debug this type of thing or understand it better, or maybe in the future, if you learn enough, designing something like HTTP3 to make the world better for everybody.
Yeah, we didn't get to talk too much about deadlines and timeouts, sadly, but I assume those are like, anytime you talk about networking stuff, I assume that becomes important. So Adam, do you want to, I guess, is that something you could talk about relatively quickly as we get near
Sure.
the end of the episode?
Yeah. So we mentioned TCP has keep alives that try to maintain the integrity, or at least make sure that the other side is still listening, even if it's not receiving data yet. That's not the most portable mechanism, and those packets can be filtered by intermediate firewalls. So a method that I prefer is to use deadlines in Go. So you can set a deadline on your connection to say that if, as soon as this deadline is reached, any blocking calls to read or write immediately return. So in that scenario, let's say I'm communicating with a client that I expect to send me data, but I don't send data very often. So I'm essentially blocking on the read call. And something happens where that client goes away, but I didn't receive a FIN, right? So I'm not receiving any data. Maybe someone firewalled off that connection or something. So I'm sitting there with this open TCP connection thinking I'm talking to another side. I could certainly enable TCP keep alives if their end supported it and my end did too. But deadlines, in my experience, are a better or a more portable way to handle this scenario. So every time I receive a message from the other side, I could push that deadline forward into the future by whatever interval, let's say 10 minutes. So that means for the next 10 minutes, I'm going to keep this open, and I expect a reply or a message to come in within that 10-minute window. Otherwise, I'm going to terminate this TCP connection. And I can set up some sort of, again, in the application layer, essentially like a ping pong, right? Or a challenge response. if I wanted to, where if I haven't heard from them in a while, I can send a ping and I expect that to elicit a response to me, which I can then use to push the deadline forward. If I don't receive one after a certain amount of time, then I may let the deadline expire, and it essentially exits the my blocking read call with a deadline exceeded error, and then I can return at that point. I can close down my end of the connection and then or attempt to reestablish a new connection to that remote side.
And this is using like the context package. Is that how you generally do that?
Now, there's on your netcon, on your con object or your interface, there is a set deadline, there's a set write deadline, and there is a set read deadline methods. So you can control either just the read deadline, the write deadline, or if you call set deadline, it sets both the read and write deadline. By default, there is no deadline in a network connection in Go, which means that you're essentially going to block indefinitely until the operating system says, we're done waiting, and closes it for you if it's configured to do that.
Okay. I was going to say that's something I think I've seen with even HTTP clients where people will set up a client to make a request. And I think you're supposed to set up a deadline. It's been a little bit, but basically set up the deadline so that you don't have something that just sort of sits there. I know that's something that people have talked
Yes.
about causing all sorts of issues where you leave it sitting open and you really shouldn't be.
Yeah, the
So
default HTTP client does not have a default timeout. It'll just block indefinitely.
So we're getting near the end of the episode. For anybody who's listening live, we're planning on doing a giveaway of, I think, at least 2 copies of Adam's book. It's going to be a physical copy mailed to you. So if you want to go follow the changelog and the GoTime FM Twitter accounts, probably the GoTime FM one's the biggest one to follow. You can hopefully get a copy of the book. And if you haven't, go check it out on No Starch's website. So Adam, before we wind this down, we need an unpopular opinion from you.
Okay.
So they'll play a little bit of music here.
So this
Get
is
everybody amped up.
this is an unpopular opinion, but not like a popular unpopular opinion, right?
Honestly, it varies. We get all sorts of different opinions. So usually they do a poll on Twitter, and what Matt always says is if it proves to be a popular opinion and it's not actually unpopular, then you have to come back on the show.
Oh, okay.
That's how
All
you lose. You have to come back on the show.
Well, let's see. This is a polarizing one. So I am a big ThinkPad fan. However, I'm also a fan of trackpad gestures. I use a lot of gestures. So I think that Lenovo should drop the ThinkPad's track point and make room for a larger, better touchpad on par with the MacBook trackpad.
So for everybody listening, what you're referring to is the little red button that's on those laptops.
And the physical buttons just below the space bar. Just get rid of those buttons. You can keep the nub. If you want to keep the nub, keep that. But get rid of the buttons, the physical buttons, and put a larger trackpad on there for me, please. That would that would be like my perfect laptop, I think.
I don't even think we can discuss this one.
Yeah, I mean, if you want to join in, either agree or disagree, you're inviting hate mail.
It's hard for me because I don't use ThinkPads, or I haven't in a long time. So I'm like, I can't really tune into this. I can't say I don't care for the buttons, but I mean, part of that's because I've been using a MacBook for so long that I'm just like used to it. I will say that occasionally if your like palm hits the trackpad and clicks somewhere, I've had it send an email because of that before. And it's just the most annoying thing in the world. And I'm like, son of a gun. My email's like halfway done. So I'm like, yeah, that email is not going to make any sense whatsoever right now. But that's a rare thing. It's only happened to me like once or twice. Any thoughts, Chris?
I'd say I think that's a good idea. Like, I think better trackpads are always nice. Like, gestures are awesome. Like, I don't know how you go back to a computer that doesn't have all of the gestures that Mac OS has. Like, anytime I have the option of like getting one of those like magic mice versus a trackpad, I'm like, give me the trackpad. The magic mouse has like this tiny little like area to do gestures in, but like I want the big area to do all of the gestures that I want. So anything that's like give me the ability to do more gestures, I'm thumbs up for me.
See, I'm pretty spoiled in that most of the time I have a keyboard and mouse like sitting there, so I'm fine. I'm used to the gestures. I use some of them, but I will definitely say that if you like natural scrolling, that you and I aren't on the same page, Chris, at all.
I just get it. Like, I don't know. I have a Linux computer that's gaming, and it obviously doesn't use natural scrolling, and it confuses my brain, which is also why I don't use my mouse as much with my Mac computers, because I just can't do it. But I can switch easily. Be like, if I'm doing a trackpad, it's fine, and then I can like scroll the right way on my Linux computer. But I can't use the same mouse to do both.
I've run into the case where I'm like helping a parent or a relative or somebody with their laptop, and I'll go to like scroll, and I'm like, why isn't it going? Like, it always throws me off, because that's like one of the first settings I change when I get a new MacBook is get rid of this.
But do you change it on your phone? Do you have scrolling inverted on your phone? Can you even? I don't know if you could do that.
It's whatever's normal on my phone feels normal to me, but I've for whatever reason on a computer, it just does not work for me. It's just not what I'm used to. I don't like it. But I think I change a couple of the gestures too. Like my setup's probably a little bit different from most, because I think I do something where like 3 fingers and 4 fingers in one direction end up doing the same thing, because I actually don't like them doing different things. It was something weird where one of the gestures that's there I don't ever use anyway. So I was just like, just make these both do the same thing. I think they both go back or something. I'd have to go check. It's one of those things where you don't actually know until you're doing it. It's like setting up a new phone. You're like, some app goes here. I don't know what, but when I go to open it, I'll remember. I don't know if I'm the only one that does that, but that's how I set up a new phone.
I've had problems with like when I'm on my iPhone accidentally dragging an app and like moving them all around, and I'm like, I don't know where anything goes, but I'm gonna know that everything's wrong, and I'm gonna be upset later when I try to open something and it's like, where is it? This is not where it's supposed to be.
All right. Adam, thank you for joining us. For everybody listening, when you do see the poll, make sure you vote whether you like his unpopular opinion, and go check out Adam's book, Network Programming with Go.
Thank you. I appreciate it.
And then we have some outro music.
Woohoo!
All right. Was that bad, Adam?
No, I mean, this is like outside my comfort zone, but it wasn't bad.
You did great. So
there was only one question I couldn't definitively answer. So, but that's all right.
I mean,
sorry.
I think that's
no worries. Listen, I'd rather tell you I don't know something than try to BS you. So,
I mean, that'll inspire people to go look up stuff themselves, I hope. But I think it's also good for people listening to realize that it doesn't really matter how much research you've done into a subject. There's probably some question you don't know the answer to. Like it's not reasonable to expect people to know everything.
I mean, I spent a lot of time looking into digging as deep as I could into the Go code to like figure out, okay, with an error that you get back from, say a con read or write, you can type assert it and tell whether it's like a temporary error or a timeout. And okay, under what conditions is an error called a set is temporary true or is timeout true? Because there's some overlap there, but there's some different connections, like whether it couldn't communicate with the other side, or there were no resources available for the request. Those types of things dictate whether something's temporary or if it's a timeout, for instance. And that's not clear in Go's documentation. The only way you find that out is to really start digging into all of the packages and find out what are the like OS level triggers for this.
I think timeouts and deadlines are like that too. Like the read deadline for, I think it's the HTTP client, is not what people think it is. And it always, I always have to go like look at it and be like, okay, what does this? I think there was like a good Cloudflare article that explains it. So I'm just like, it's not what I think it is. So I don't have to go read that article to remember what it is. So we don't set this wrong and then mess it all up.
It's especially hard when you don't do it that often. Like if you do it like once a year or something, you're just like, now I got to go remember what this one thing does and make sure it's set right. And in some, I don't know, especially in big organizations where there might be something that already does a lot of that for you, you're just like, okay, I don't have to worry about this.
Well, when you're getting paged that there's downtime, you won't forget it. You know, like if you made that mistake because you don't do it very often, you won't forget it after that.
Yeah.
Yeah, that'll make it stick a little more.
Yeah, I feel like if I was going to have an unpopular opinion this episode, it would probably be that people need to build their own networking protocols more. Not like build TCP and UDP, but build like things on top of it. I know I said that everybody should probably just use HTTP, but honestly, I'm kind of tired of people not really using HTTP as it should be, and just like, I have a JSON blob, I'm gonna stick in the body, and that's all I care about. I'm not gonna deal with headers or any of that. I'm like, then don't use like HTTP. Go make up some simpler protocol to shove your JSON object over the wire.
Yeah, I think it's a great exercise to take UDP and try to make it reliable. I mean, at the application layer, try to make it reliable. And it's, in my opinion, it's a hard problem to solve, at least to do it well. It's probably easy to do over, like, say, your own network. But if you're trying to do that, you know, across the world, yeah, it's a different ballgame.
I was gonna say, when you throw in the real internet, that's when it gets tricky, because I've even seen people doing HTTP clients where everything works great, and then they like throw it on the internet and everything stops working, and they're like, "What's going on?" I'm like, "Well, on your local network, it's nothing like there's no delay or anything. Like everything's just pretty much instantaneous, and in the order you send it. Maybe not always, but pretty much. So it's like a very different scenario to like when you actually go someplace with like low internet speeds. And because I've heard some people tell me that different companies, I think Facebook did this, where they would actually have like one day a week where they'd actually crank down everybody's speeds on their Facebook apps on their phone, I think, to like replicate, I think it was Africa or one of those places with lower internet speeds. And the goal was so people sort of understood how their apps worked when you introduced those latencies and things like that they experience, just like actually try to design around it. Because without that, if you're in the US, like on a smartphone, your experience is vastly different than what it is somewhere else necessarily.
Yeah. I think there's some irony too in that there's like all these levels of packet framing, right? There's like Ethernet packets and IP packets and TCP packets. And then we have like this stream layer that's meant to be like, oh, this is easier for you to use. And then you immediately have to turn it into like a packet or a frame of some sort. Like, as you mentioned, it's like, how many bytes do you need to read? It's like, I don't know. I have to invent some way of like reframing this thing. Kind of feels like there's probably a better way for us to solve that problem than what we came up with. It's just like, I don't know, throw streams at people. They'll be able to figure it out and make it work.
I didn't ask it in the episode, but one of the things that always baffles me is that I feel like we tend to make way too many standards for things. And the fact that we just have TCP and UDP kind of shocks me sometimes, that somebody didn't come up with some third way and be like, let's do it this way instead.
I mean, there are just no one, like there's SCTP, which kind of merges UDP and TCP. It's a weird protocol, but like not really used that much. I think part of the reason, ironically, is that TCP and UDP are probably the only things you can get through most of the internet infrastructure. Like, for the most part, the firewalls just block everything out. So you can't send as much stuff. We can't send as like new protocols over the internet. So it's just like, let's shove everything into TCP and UDP and then wrap it in TLS of some sort so that things can't filter out stuff in between.
Yeah, I imagine that'd be a challenge in the sense that the internet is so big at this point, and expecting people to swap out every router in the world and like actually change those would be like, that's not going to happen.
You wind up with like things that seem like good ideas, or there's like things that get stuck, like the refer header in HTTP being spelled wrong, or what I always find it interesting, I still like talk to people and they're like, oh, my like internal headers for HTTP are going to start with X. It's like, I don't know, it was basically a decade ago that we figured out that was a bad idea. It sounds good at first, like, oh, they're experimental, but then everybody implements them. So then you can never get rid of the X. So what's the purpose of having the X then? And it's like, oh, just name them well from the beginning and you'll be good. You don't have to prefix things with X.
I imagine that's part of the reason why Google can get away with experimenting with some of the stuff, is that they probably cover such a huge chunk of the network of the internet that they can get away with a lot.
Yeah, and there's some good bones there too. I mean, with HTTP, one of the reasons I think it's such a cool protocol is that it has built into it the ability to upgrade to new protocols, which is how like HTTP2 works a lot of the time. It's just like, here you go. Here's like an upgraded protocol. You can go to HTTP3 or HTTP2. You can go to WebSocket. You can go to HTTP3 or whatever. It just like enables you to upgrade in ways that you can't really do with other types of